Hi, welcome to Project Geospatial. This is Adam Simmons with the Geospatial Frontier Virtual Technology Fair, hosted by Project Geospatial and partnered with the American Geographical Society. Here with me for this session is Nathan Kundtz. Is that how I pronounce it correctly?
That's close enough.
Oh boy. Okay. Well, you have to correct me on that one. But here with Rendered.AI. And Nathan, if you can kind of give us a rundown of who you are specifically, and then we'll dive into the company.
Yeah, no, thank you, Adam. And it's a pleasure to be here. Thanks for having me. My name's Nathan. I'm a physicist by training and, as I like to say, an entrepreneur by birth defect. So after finishing my education, actually the first company I started was the company Kymeta that I'm best known for. And we delivered really the first electronically scanned VSAT solutions into the satellite communication space. And that gave me a lot of exposure to what was happening in satellite and in communications, and by connection also to what was going on in the commercial geospatial industry. And so I transitioned that company over to a growth leadership team about a year and a half ago, and have really since then been bitten by this question of how do we address some of the data challenges that are being presented as we get more and more real data from these new platforms. And as I explored that problem and really dove into it, it was clear that we had a gap where we weren't able to address some particular challenges. In particular, we really have difficulty identifying edge cases in that data when it comes back. We have a lot of challenges when we're trying to do next generation systems engineering with new sensors and new scenarios. For instance, as we're trying to do Earth observation outside of the sun synchronous orbit. There are massive data labeling choke points in the industry today, which are creating challenges not only with the ability to get access to labeled data, but also to improve accuracy, because we end up being limited by human accuracy in labeling data. And then, of course, the industry is rife with data sensitivities, and all of those form a tremendous set of challenges for anybody trying to do artificial intelligence or machine vision in the industry. And so I started tackling this challenge with a small team, and really settled on synthetic data as the best way to address this. And in particular, physics-based synthetic data. So using what are called priors associated with our understanding of physics and what things would look like if we were able to image them with the sensors that we have. And I think I should say first, that is not a new idea. So synthetic data and physics-based simulation are very old and well and tried and true methodologies. But there's a very different set of emphases that comes to fore when you're starting to talk about that in the context of AI. And we didn't see tools that really met those challenges. We tended to see tools that were either really intended for video games and maybe content in movies, and other tools that were really intended for sensor design, but nothing that really was in this synthetic data for AI training space. And there's a few differences. And so, like, if you get into the optical simulation world, there are tremendous engines out there for physics-based simulations, as you would see in movies or video games, but they really lack atmospheric physics, right? They lack some of the things that really drive what we see. Now, there are some tools that are available to the government for that kind of simulation, but they're not GPU accelerated. And so you don't have this kind of mix of how do you get a lot of data that's physically accurate enough to actually train on. That problem is even worse when you start to get into radar and synthetic aperture radar data, where you just don't have the simulation tools necessary to achieve the kinds of large scale simulations necessary for this kind of training. And I could go on and on when we get into kind of thermal and IRs. I won't bore your audience to death here. But needless to say, what we found was we wanted to start with there's a lack of the right kinds of models, and we felt a lack of just simulation software that was purpose built for this, as opposed to some other applications. To layer onto that, in this world of synthetic data generation, we need to do more than just simulate as seen, right? We're trying to generate lots of diverse images for training. And that's a very different problem, and it comes with its own set of kind of procedural generation tasks which are typically not part of the workflow in any of these other tools. And so we've layered on a whole set of libraries and continue to build libraries associated with world building and procedural generation. And that allows us to get data sets that are not only very diverse, which is useful for both training and validation purposes, but also it puts the power in the hands of the user to drive that diversity and really identify what they want in their data sets. And then finally, we felt like the whole workflow needed to be revamped. The way in which these simulations are created, again, has been designed for other purposes. And the tool set needed today is for rapid iteration of large-scale data generation and then very quick pipelines into training modules and testing modules. And that just really didn't work. If you're doing a simulation in your desktop, you're typically talking about then trying to pipe that over to somewhere else, maybe up into the cloud, maybe to other collaborators, using a ton of bandwidth and typically slow. And so we've focused on a cloud native architecture, and we've included in the overall approach a managed high performance compute environment, data set storage and management, and introspection and exploration. And then we also provide algorithm templates, because oftentimes what you really want to know is not how good does my simulation look, but how effective is it in actually training an algorithm to detect something. And we've built the whole thing in order to really speed up that process in answering that question.
Well, that's a great introduction to Rendered. So talk about the company itself. When was it founded, and where are you right now, and where are you at right now in terms of business?
So we were founded last year, and right now we're in the place where we have the first iteration of our tools deployed and are working with early thought leaders in the field to make sure that we're really addressing the needs of the industry. I would say, I think, and anyone listening would probably agree, synthetic data is really new. And figuring out exactly what the best ways to leverage synthetic data as a tool is often at the bleeding edge of what people are doing with artificial intelligence. And so we have been working with the folks that we feel are the best, although are certainly open to expanding those partnerships. And you'll be hearing more from us in the form of blogs and white papers as we start to be able to talk a little bit about what we've learned.
You mentioned simulation of synthetic aperture radar. Can you dive into that a little bit more? What kinds of data sets are you using to help simulate the radar? Or is it literally creating an image from scratch to simulate it? Is it taking other imagery and transforming it into a radar image? What could be involved with a process like that?
Yeah, that's a great question, because there are a lot of different approaches out there. I personally don't feel like taking an optical image and trying to ask, what does this look like from a radar perspective, is a good approach. I think you're just missing almost all of the physics that's taking place. And while you might get something that looks interesting, a lot of what you really need for instance, automated target recognition in a synthetic aperture radar image has a lot to do with specific backscatter features that need to be captured. And so we actually leverage 3D models of both cities and objects, and we give them material parameters that are appropriate for radar. So conductivity, permittivity, permeability, and maybe really importantly, we have different ways of handling the microscopic roughness of those surfaces, which often dominate what you see in those scenes. And our approach is to actually go ahead and simulate the entire radar process. So we actually simulate the transmitter, the propagation of that wave, interacting with the surface, and then reflecting back to the receiver. And we make, as you might imagine, we make some approximations that we think are appropriate in order to speed up the compute of those images. But we can now do multiple city blocks in about half an hour on a single core. And so, that leaves a lot of room for expansion and doing very, very large data sets. And so I've been excited about that. But we've had to make some pretty big technology advances in how to actually carry out those simulations, how to handle very electromagnetically large mesh elements, which may be getting a little bit into the weeds here, But I'll just say there's a lot that goes on behind the curtain when you're trying to perform that kind of a physics-based simulation.
Well, I'm sure that goes into creating the models themselves, correct? Around the use cases of the different customers that you have or are looking at. And you mentioned city blocks, which tells me that maybe you're looking more at urban environments. But what other use cases are you looking at as well? Between maritime or some type of critical infrastructure globally, things like that. What other use cases are you looking at for trying to use this concept?
Yeah, for synthetic aperture radar specifically. So synthetic aperture radar really mirrors what you want to use Earth observation data for. And so it's a combination of cycles of life, trying to understand the economy, some trying to understand crops and crop management, often shipping and tracking shipping. We've recently had a lot of interest in iceberg detection, which is something that I think still creates a lot of trouble. And the reason people go to synthetic aperture radar is twofold. One, it turns out that if you're trying to image the Earth with an optical camera, you have a few problems. One is that half the Earth happens to be dark, and you can't see it, and so that creates a problem. And then the other challenge that you have is approximately 70% of the Earth is covered by some form of cloud cover. And some of that you can see through to a limited extent, but it nonetheless obfuscates the image. And there's only so much you can do with image correction. And so moving to an active sensor like synthetic aperture radar allows you to image not only when it's dark, but also to see through that cloud cover. And that can be critical not only when low latency is important for an application, but also in some areas where cloud cover can be perpetual for whole seasons.
So what resolutions do you simulate right now? Does it matter at all, or are you trying to actually simulate the current sensors that are capable in the field right now? 0.5 meters, things like that.
We've been working with some of the commercial companies building these sensors and deploying them to actually calibrate our simulations to what they see from their sensors. And so a lot of that's happening in X-band with resolutions kind of in the half meter range.
Okay.
And as you say, some of them are, as you may know, some of those images end up being restricted based on resolution. And so, it becomes doubly important to be able to provide synthetic data for training because the real data may not be shareable.
Absolutely. I mean, but then also just, I wonder how much you just jump ahead, capable of simulating data that's much lower so that you're preparing for emerging sensors too, or how far ahead. But I don't want to focus just on SAR or radar in general. You touched on a few other sensor types too, right? Infrared perhaps, and maybe
that's right.
Other things.
So wrapping up on SAR, I would say that does also extend to we've gotten some extension of those utilities into some remote occultation sensors and some really new flavors of sensors where there's a simulation and systems engineering task ahead of the actual building of the sensor. When you get into thermal, it's really interesting. So the actual propagation you can handle with a lot of the rendering engines that are available off the shelf. And you can even manage emissivities in that way. But what's missing is an actual thermal model of what's going on. So doing solar loading and managing the various types of energy transfer between surfaces are typically not carried out, and those can be quite important. So if you're looking at a scene with a thermal camera, you'll see that something had been there maybe 30 minutes ago, right? If you park a car on a hot day, it's much cooler underneath that car. And once that car moves, that spot is there for some time. And that actually can be really important to tracking behaviors and understanding what's going on from that kind of imagery. And so what we've done is of course, we use the best in class rendering engines when we do these simulations, but we layer on top our own thermal simulation capabilities so that we can capture those effects.
So does this also translate into what we'll call full motion video versions of infrared, or perhaps even full motion video SAR?
Yeah, absolutely. Absolutely. So everything we're doing is amenable to full motion. What I would say in SAR, the image capture process is actually a time-dependent process. It's not kind of, a pseudo instantaneous snapshot like you would get from a camera. And so what it means to manage full motion video in SAR is really to allow the image to move throughout that capture process. And we have been doing that. And we think that that's really important when it comes to looking at things like sea state, because you're actually the objects on the ocean and the ocean itself will change over time. And there's ways to manage that stochastically, but we think it's better to actually capture that physics in the simulation itself.
Excellent. So there's just kind of to dive a little bit more into the output and what kind of deliveries or standardized data formats do you push for the simulated data?
So in most cases, people are working from a PNG format, from a standard image format. The exception is synthetic aperture radar, where we provide both what the term of art is a compressed image, which is something that an analyst might look at, as well as the raw data output. On top of that, we provide a variety of different annotation formats and try to be flexible when it comes to that and meet the needs of the customer's machine learning algorithms. I'll say one of the benefits from approaching data generation in this way is you get a huge amount of additional metadata creation potential. So you can grab a lot of information about what's going on in the scene. And so we make it really easy for our customers to kind of go into the actual simulation pipeline and say, okay, well, I also want to know that. I also want to know that, and get access to that data on the back end.
Sounds good. Now, so what kinds of things along the way as you're developing this has kind of surprised you? Kind of your big aha moments that you're kind of like, whoa, we can, what are your big epiphany moments as you're exploring your new tech?
I think we've really started to understand more about the ways in which synthetic data can be used. I think the most obvious thing that happens when you get into this is you say, okay, I'm going to produce data and we're going to improve a detection algorithm with that data. And that certainly is by far the clearest use case and value proposition. But as you start to dive in, you realize there are a lot of folks out there with data sets that don't fully understand the data sets that they have. And so using synthetic data becomes a really powerful tool to understand what you've actually got in the first place. And that might be doing something like taking synthetic data and doing what's called a principal component analysis and comparing that to metadata to just really understand what is driving the key features that a machine vision algorithm would see. It's something where you wouldn't have that information in a real image, but that gives you some understanding of what's going on. In another application, we're driving a detection that's really at the limit of even what a human could see. And you have these fundamental questions like, can an algorithm detect this or not? Becomes just as important as maybe improving what the algorithm's output can be. And so more and more, I see us getting pulled into what feels to me like next generation systems engineering, where it's not sort of give us the magic data so that we can improve our algorithm. It's, hey, we really need to understand the data we have. We need to understand the algorithms that we have. We need to understand their limitations. And this is a vehicle to do that.
Awesome. Good answer. Now, aside from, those aha moments, I like to ask a parallel question is, what are the biggest challenges that you are facing right now for getting this up and going, and that you're going to overcome over the next year or two?
Sure. I mean, the biggest challenge in many ways to market growth right now is just that we're very early. And that's not specific to us by any stretch, but the industry around synthetic data is very early. And so there's a lot of, how should I say, the amount of knowledge that our customers have on how they can use synthetic data is highly varied. And so there's a lot of education that happens up front, both on their part and frankly on our part. And so we've been trying to focus on a business approach here, which is exploratory, and can really support a variety of different directions that our customers may need to go. And we're trying to remain as flexible as possible in terms of how we've built out the tool and address new use cases that come up. But I expect that it will continue to be early days for the next year or so. But that as we really get into this, not just interest in artificial intelligence, but need to deploy artificial intelligence as part of macro programs, this need for real systems engineering is going to be paramount. And frankly, I don't know how you do it without synthetic data. So I see that coming.
Now, so what kind of caught me at the beginning of what you talked about Rendered and what you're doing is what other industries. You mentioned the gaming industry is big into simulated data, and you mentioned one more as well. But what fascinates me is I keep on getting comments here on the side, not with this video, but in industry in general. When we talk about machine learning and training, there's been a lot of skepticism about using simulation data, even though that, do you think it's a lack of awareness of how other industries are using it, how far developed it is? What do you think the pushback in our industry has been over the years for just kind of getting on the bandwagon with this?
Yeah, well, I think that there's a lot of synthetic data out there that's, I'll just say politely, right, hasn't been done as well as maybe it could have been or should have been. And so if you're generating synthetic data by sort of photoshopping in images on top of images, you get all these weird artifacts that, machine vision algorithms tend to queue on. And some of the early results in those attempts really highlighted that. As we get into synthetic data generation in its current form, we have a lot of tools to overcome those sorts of artifacts. Of course, we start by doing, the full physics simulation of the environment, and that doesn't lead to the same sorts of artifacts. But we can also do things like domain transfer, and there's a lot of knowledge being developed on that to make those synthetic images have a similar character to those that are taken from the real world. But really, we still see this as an iterative process. And so my feeling right now is that anytime somebody says, hey, I'm just going to give you a synthetic data set and you're going to train on it, and boy, it's going to work right off the bat, I just think they're wrong. We just don't think about the problem like that. Because what we've found is you're going to get a data set and you're going to say, well, this helped here, but I'm not yet working over here, and you're going to want to introduce new features to that data set. And we had a particular program that we worked on with a company that wanted to identify cranes. They wanted to identify cranes in visible remote sensing imagery, and was really difficult because you're sort of talking about very low pixel counts and kind of these little yellow streaks. And so if you train up an algorithm using as realistic as you can imagery to do that, what you find is that you've created a yellow streak detector. It's like, oh, well, it's not quite what we were after. So we actually started generating images that were completely fictitious. So we actually took a huge amount of different geometries that were all, yellow to brownish and streaky. And we layered on cranes, and we found that by doing that, we were able to provide a portion of the data set that really helped the algorithm key in on those geometric features that were specific to cranes and didn't reflect other types of geometry that might be seen in the image. But that's something that you discover as part of an iterative process. And that's one of the reasons we feel like it's so important to deliver a tool that generates synthetic data and continue to be a partner with the customer as they explore that, rather than approach this as a kind of, here you go, I hope it tastes good approach to synthetic data.
Excellent. So I have one or two questions coming in off the side from me. And so the first one is how much this technology, I think folks are kind of really impressed about some of the best practices. Since you mentioned the gaming industry, how many best practices are you adopting from that side of the house? And I'll ask the second question. That's a little bit more complex and a different topic after you're done with that one.
Sure. So we've been leveraging what we can from the gaming industry. We have focused mostly on open source rendering engines because that allows us to go massively parallel in the cloud. And so, there's a large number of them. We've really focused on those that are physically accurate, and where we can actually get into the code and make sure that they're handling various effects in a way that we feel comfortable with, particularly when it comes to things like atmospherics. And so, we have used engines like Unity, but we tend to shy away from them because they're really designed for real time. And this problem is not a real-time problem. And so we have focused more of our attention onto those rendering engines that emphasize physical realism.
Awesome. So the other part is you also mentioned how you're trying to make the process more usable for customers, right? What does that mean? Is that usable for data scientists working with the data, or we're talking about the complete end user here who has to take these perhaps take the machine learning results and use it within their mission workflows?
Yeah, absolutely. I mean, I think it's a team-based approach, and we see this as a collaborative process. And so there are a few pillars that we've adopted when trying to address how we can get people to have as easy as possible in what is a difficult problem. The first is we've actually built up a visual programming language around defining what we want in these simulations, and we work with customers to fine-tune that for their specific applications. But it makes what is an incredibly complex scene generation process a few drag and drops and nodes that allow us to really powerfully adjust what's going to be present in those simulations. In terms of the end user, we focus on the machine vision or data scientist as our end user. And so we sort of think about this as a tool which can be driven via a web interface, and we encourage people to start there. But that we've also built in API access to every single core piece of the environment, so that you can sit at a Jupyter notebook and really drive the whole environment from there and automate the process. And we actually encourage people to do that by providing templates of those Jupyter notebooks, so that you can click through a wizard and then get to a starting point right away. The objective here is to give that data scientist the tools they need to be responsive to the senior level person that's asking them for specific information. And maybe I'll give you an example. We often have this conversation about understandable AI and trying to understand how did the AI come to some conclusion? I'm sure you've covered that a number of times in these. And what we found in working with folks is what they really want to know is, how do I know when it works and when it doesn't? Like, if it's a person, I can kind of either through my own intuition or by, understanding the people involved in the process that they're going through. Not only can I understand when it's likely to work, when our approach is going to work, but there's a person there who takes accountability when it doesn't. And so we feel like in order to do that for AI, we need simulation tools that allow that data scientist to answer those same questions. And drill into when does it work, when doesn't it, why, which features is it keying into, and how do we make the right trade-offs, right? What do we want and not want in this data set in order to get the right mix, for instance, of selectivity and accuracy?
Do you make another algorithm to judge the process, the main one as it's going through and trying to identify things? Is that an option?
Yeah, you're getting into a really exciting area that we're just starting to explore, which is really closing the loop, which is saying, hey, okay, if I build X data set, I get Y result, but now that this is all automated, I could actually say, okay, but now I can edit what went into that X data set and start to do things that lead into unsupervised learning. And I'll say, we're working with folks who specialize in that area and have the intention, it's not available yet, but have the intention of creating those templates so that, again, if you adopt the tool, you'll be able to set up your simulation environment and then move directly into, okay, here's a template for how I would do that closed loop unsupervised learning.
Awesome. Well, so I don't think I have any more questions coming in, but do you have any other things that you want to talk about for Rendered, last minute plugs before we wrap up?
Yeah, again, it's early days. And so we're interested in working with those folks who see themselves as thought leaders in this industry. And so if any of your audience fits that and would like to kind of work with us and explore with us what's possible using synthetic data, we'd be delighted. And I'm sure you can put my contact information out there. There's not much of a website right now, but coming soon.
Great. Awesome. Thank you very much, Nathan, for joining us. Nathan with Rendered.AI. And we will put your website, as long as any other details you want us to put in the show notes. This is Adam Simmons with Project Geospatial, the Geospatial Frontier Virtual Technology Fair, signing off. Thank you for listening, everybody.